Hello, this is Professor Keene. In my previous lecture, I introduced the conservation of momentum, which Newton says follows from his laws of motion in his Corollary 3. In this lecture, I'm going to talk about Corollary 4. This Corollary Roman numeral 4. And I'll write it out first, and then I'll explain what it means. Corollary 4 states that the common center of gravity, we'll have to remind ourselves what that means, but the common center of gravity of two or more bodies does not alter its state of motion or rest due to, or I'll say by the action or the force of bodies among themselves. Okay, the common center of gravity of two or more bodies did not alter its state of motion or rest by the action of bodies among themselves. So in other words, if you have two or more objects and you compute where its center of gravity is at a particular moment, and then if those three objects are moving in some complicated fashion, and you compute the center of gravity at each moment in time, then that center of gravity motion, so how fast it's moving and the direction it's moving, does not change, provided the only forces acting on these bodies are the bodies acting on each other. That is, there are no external forces on the system of bodies. Okay, so let me do an example that will hopefully clarify this. So here's an example. Let's suppose that we have a table, and this is a very slippery table, so we can assume that there is no friction force that's going to slow down objects sliding on it. And let's suppose that we have, I know it looks like it's floating, but that's supposed to be right on the surface of the table. Let's suppose we have a block of mass 2 that is moving with the speed of 3. And let's suppose it's moving toward another block. So this is, I made a gap here so it looks like an air hockey table or something. So these are moving without any friction. This has a mass of 1, and its speed is initially 0, so it's not moving. And we put a little piece of gum on this. So this is a piece of gum, so that when this block hits that block, it's going to stick. Okay, so this is a table. And here's the question. The question is, what is the motion of the center of gravity before and after the collision? So what is the speed? Let me ask it this way, not the momentum, but what is the speed of the center of gravity of this two-block system, both before and after the collision? So let's remind ourselves what we mean by the center of gravity. So this is a little aside here on center of gravity. So if we have two objects, for example, a block of mass 2 and a block of mass 1, and we wanted to find where the center of gravity of these two are, we could imagine putting these on the ends of a seesaw or a balance and finding the position you have to put the fulcrum in order to balance them. And if it's a 2-to-1 ratio, then the distance from that block to the fulcrum is going to have to be 1, and the distance from the fulcrum to that block is going to be 2, so that the torques, that is the weight times the distance that's trying to make this rotate counterclockwise, is balanced by the torque, that is the weight times the distance that's trying to make it rotate clockwise. So the center of gravity location, at least the horizontal center of gravity location, is going to be closer to the block of mass 2 than the block of mass 1. Okay, so that's a reminder of how to get the center of gravity. It's sort of the balance point, if you will. Okay, now going back, so this was an aside. what is the speed of the center of gravity before the collision? Well, you might think that it's moving because this block is moving with the speed of 3. Perhaps the center of gravity also is moving with the speed of 3. So let me just ask that. Is the center of gravity moving with the speed of 3 before the collision? Many people think this. And the answer is no, it is not. It's going to be moving slower than a speed of 3. How do we know that? Well, think about it for a moment. If I were to draw the position of the center of gravity, it's going to be closer to this guy than to this guy. So it's going to be kind of over here. That would be the position of the center of gravity at this moment in time. As this block slides to the right, the center of gravity is going to move to the right. If it's moving at the same speed as that block, then as the block moves, it's going to stay the same distance away from block 2, and eventually when they hit, the center of gravity is going to be way over here. It's going to be to the right of both blocks, which doesn't really make any sense. Rather, what has to happen is this center of gravity has to move at such a speed that the ratio of the distances between this and the center of gravity and this and the center of gravity always has a 2-to-1 ratio. So it's going to maintain, so this distance from here to here compared to this distance from here to here always has to have a 2-to-1 ratio. Okay? And that implies that the center of gravity speed is going to be somewhat slower. Okay, so how do we find the speed of the center of gravity before the collision? Well, the solution, how we figure this out, we're going to use a trick. You might be able to figure this out on your own. But the solution, I'll give you a strategy for doing this. The solution is to find the speed of the blocks, of the stuck together blocks after the collision. Whatever speed that composite 2-block system has, right? They're going to be kind of stuck together. They're going to be moving with some speed after the collision, right? That's going to be the final velocity. That is going to be the center of gravity speed after the collision. Whatever the speed of those 2 blocks is moving at, that is going to be the final velocity of the center of gravity. And now, using corollary 4, we know that the common center of gravity does not alter its state of motion or rest by the action of the bodies among themselves. In other words, whatever the center of gravity speed is after the collision, that must have been the center of gravity speed before the collision. So we can use conservation of momentum, corollary 3, to find the final velocity, and that gives us, or that provides, the initial velocity of the center of gravity. Right, so because it cannot suffer a change due to this collision. Okay, so how do we use conservation of momentum? Well, we know that conservation momentum says that the momentum initially of this system of blocks has to be equal to the total momentum final of the system of blocks. This is conservation of momentum, or his corollary 3, right? What do we mean by the initial momentum of this system? We mean the momentum of the block having mass 2 initial plus the momentum of the block having mass 1 initial. And what is the final momentum? It's the momentum of block 2 final plus the momentum of block 1 final. Well, what's the momentum of block 2 initially? Well, that's plus 6, right? Because you multiply the mass times its speed. What's the momentum of block 1 initially? Well, that's 0 because it wasn't moving. What's the momentum of block 2 final? Well, it's its mass, which is 2, times whatever that final velocity is of block 2. What's the momentum of block 1? Well, it's its mass, 1, times the same final velocity, because they're stuck together. They've got the same final velocity, right? So let's write this. Plus 6 equals, let's factor out the final velocity, and then write 2 plus 1, or the final velocity 3 times the final velocity equals 6, or the final velocity of those blocks is going to be 2. So this right here, the final velocity of these blocks stuck together after the collision is 2, which means that because the center of gravity speed cannot change as a result of the collision, that means that the initial speed, so the initial speed of the center of gravity is 2. So we used conservation of momentum to figure that out. So that is corollary 4. Okay, I'm going to stop there.